Okay, so the last section we're going to take a look at is 11.3. And 11.3 is on what we call the binomial theorem. It's kind of an application of a series. Okay, we're going to look at summations again today, but very special summations. Okay, what I want to look at is taking a binomial and raising it to a power. If you do this out, it will be a series. It's something plus something plus something. What do you get if you take a plus b and square it? The whole thing. Yeah?
A squared plus 2ab plus b squared?
Perfect. A squared plus 2ab plus b squared. And that is a series. It's a sum. It's a summation. It's a finite summation. It's only 3 terms added together. Now, if you do a plus b cubed, that would mean you'd be taking what you had right here and multiplying it by another a plus b. So you'd have to distribute a to everything, then distribute b to everything, and that's what you'd get down below. Okay, so I'll do this one, but that is going to be the last one that I do out by hand. So you're going to end up with an a cubed, a 2a squared b. You're going to end up with a ab squared. You're going to end up with an a squared times b. You're going to end up with a 2ab squared. And then you're going to end up with a b squared times b. That's a b cubed. So that should be what I have written right there when I combine my terms. A cubed, got it? 3a squared b. Well, there's a 2a squared b and a 1a squared b. Add those together and you get 3a squared b. I have an ab squared and I have a 2ab squared. Add those together and you get 3. And then I have a b cubed. Okay, so I'm going to do this out for a couple more. I already have it done out for the 4th and the 5th. And what I'm more interested in here is not to keep doing it out, but the pattern. I would like a quick way to be able to do a plus b to the 20th. But I don't want to have to do it like this. So if you look at the kind of like the factored version on the left and the expanded version on the right, does anybody see a pattern? There's a few patterns here of something that's going on. Yep.
Exponents are decreasing by 1.
Which exponents are decreasing by 1?
The next one. So we can go from 5 to 4 to 3, and then it increases by 1.
So the exponents on what letter are going down by 1? A. And what's happening with the exponent on B?
Oh, it's increasing.
It's increasing by 1. So yeah, the exponents on A start at the highest number and go down till eventually the A is gone. And the exponents on B, well, it's gone at the beginning, and then they go up from there. Okay, so that's a pattern with the exponents. Did anybody notice anything else? Yep.
The highest exponent is equal to what's what the original equation is being put to the power.
Yeah, yep. In fact, if we generalize that a little bit, the sum of the exponents on every individual term is always equal to that one. The exponent here is 5, 4 plus 1 is 5, 3 plus 2, 2 plus 3, 1 plus 4, and 5. So if you add the exponents together on any term, they're always equal to the original exponent that you had. How about the number of terms? How does the number of terms compare to that exponent? Yeah?
Is it always one more than what exponents?
Yep, it's always one more. So if you raise something to the second power, you get 3 terms. To the third power, you get 4 terms. Okay, so there's a few different patterns. Now, let's look at the numbers in front of each term. Yeah?
The second term in each line, or I don't know if you want to call it term, but like, so it's 3a squared, and then it's 4a cubed, 5a to the 4th power. With the second term, the coefficient goes up by 1.
So yeah, the coefficient of the second term is always going to be the exponent. That will always happen. Yeah. So let's look at all the coefficients. What are all the coefficients in the top one? Let's write them down. One, 2, 1. Okay. What are the coefficients in the next one?
1, 3, 3,
1, 3, 3, 1. And then the next one?
1, 4, 6, 4, 1.
1, 4, 6, 4, 1. We saw those numbers before this week. Does anybody remember where we saw those numbers? Yeah?
Pascal's triangle?
Those numbers come from Pascal's triangle. Yep. So some of the patterns, I think, did we find them all? There's one more term than the exponent you're raising to. We've got that one. The sum of the exponents in each term is always the power that you're raising to. Yeah, we got that. The degree of the A is going down by 1, and the degree of the B is going up by 1. But the most interesting pattern is with the what's happening with the coefficients. The 1, 2, 1, 1, 3, 3, 1, 1, 5, 10, 10, 5, 1. Those numbers, those coefficients, are coming from Pascal's triangle. So remember Pascal's triangle. I gave you guys a diagram of that, I think, on Monday. Maybe it was Tuesday. So Pascal's triangle basically has 1s going down the sides of it. And then each number in the triangle is the sum of the 2 directly above it. So 1 plus 2, that's how you get 3. 6 plus 4 is 10. And if you notice, the rows in Pascal's triangle are symmetrical. Once you get to the halfway point, you have the same numbers repeated in the opposite order. 1, 5, 10, 10, 5, 1. Right? 1, 6, 15, 20, 15, 6, 1. Sometimes there's a number that's right in the middle, and then you have like an even amount on each side. Sometimes there is no middle. It's like the middle would be right there. 1, 5, 10, 10, 5, 1. So really, once you know the first half of a row in Pascal's triangle, you automatically know the last half. Just reverse the order. So each entry in the triangle is the sum of the 2 rows above it. It is important how we keep track of what row we're talking about. The very first row in the triangle is called row 0. Okay, the reason we call it row 0 is because it just helps some patterns we're going to look at make more sense. Okay, so the first row is row 0. The first column is also column 0. So if I was looking at this number right here, I would say that that is row 0, 1, 2, 3. That is row 4, column 0, column 1. That is row 4, column 1. Any question on the notation of how we describe a position in this triangle? Just make sure you start with 0 for rows and columns. And that's the pattern that I really just pointed out to you on this page. If you want to expand a binomial to the 3rd power, then to get the coefficients that go in front, you should be looking at the 3rd row. 1, 3, 3, 1. If you want to expand something to the 5th power, then you want to take a look at row 5. 1, 5, 10, 10, 5, 1. So this works okay if you got a small power, but what if you add like to the 35th power? So you're going to make this triangle to 35 rows? I guess you could, but chances of you getting that done in a decent amount of time and not making any mistake, not that good. So again, this works okay, maybe up to like 7, 8 rows, you could reasonably make this triangle. Beyond that, we're going to have to figure out something a little bit more creative. Okay. All right, well, let's try using the binomial theorem to do some expansions. Okay. So I have row 6 already done out on the triangle, so we're not going to have to worry about doing that out. We just have to put everything down the way it goes. Okay. What's going to be the coefficient of my first term when I do a plus b to the 6th? Yep, it's going to be a 1. And what's going to be my exponent on a?
6.
Yep, a to the 6th. What's my exponent on b?
There's no b for the first term.
There is no b for the first term. It's not there yet. Plus, okay, what's my next coefficient?
6
6.
with a to the 5th and b.
Mm-hmm. Okay, next term?
15 a to the 4th b
b
squared.
squared. Okay, someone else give me my next term.
20.
20. What's the whole term?
20a to the 3rd, b to the 3rd.
E to the 3rd. Okay, next term after that.
15a to the 2nd, b to the 4th.
15a to the 2nd, b to the 4th. Okay, Zach, what about my next term?
6a to the 1st, and then b to the 5th.
A to the 1st, b to the 5th. And my last term.
Would it be? Would be a to the 1st power and then b to the 6th?
I already have a to the 1st right there.
B to the 6th.
Just 1b to the 6th, which is just b to the 6th. Okay, bless you. Okay, so I'm not sure what you think, but I think that's a lot faster than trying to do a plus b times a plus b 6 times and then foiling it all together. But that's what you would end up with. Okay, and that is a series. It's a sum of 7 terms. It's a finite series. It's a very special series. It's the series when you expand a binomial to a power. Okay, that's a plus b to the 6th. Let's try this one. 2x plus y to the 4th. Okay. So this one's going to have a few more steps to simplify at the end. Because in the binomial, the first term, the a, it has 2 factors in it. Okay, so we might see rules like power to a power come up, and we might see a rule like product to a power come up. All right, let's start with our coefficient. What's my first coefficient going to be?
It's going to be 2x.
First coefficient is 1. And then what's going to be in parentheses right here?
2x to the 4th.
2x to the 4th. So it's whatever is here, whether it's a single term, a single factor, or more than one factor. You put that whole thing to the 4th, and that's it. Okay, what about my next coefficient?
Is it 2x, 3y?
I need a coefficient first.
4.
4. So go to the triangle first. And then what goes here?
I was saying x3 to y1, but I don't think that's it.
No, it's not x cubed. Yep.
2x
Just 2x, because these are in separate parentheses. You're never going to have an x and a y in the same parenthesis.
As cubed.
2x cubed, yep. And what else?
Would be times y there.
Times y. To what power?
Third, or second.
No power. It's just 1.
To the first. Yep. Okay, next coefficient would be
6.
6. And then in parentheses,
2x to the second.
2x to the second.
And times y to the second.
Y to the second. Yep. Okay, next term. 4.
2x. Just 2x.
Just 2x to the first.
Times y to the third.
Y to the third. And the last term.
Or just be
Yeah, just be a 1y to the fourth. Okay, now we got to simplify that a little bit, right? Remember, when you have a product to a power, you raise each factor inside to the power. So what's 2x to the fourth?
That'd be 16x to the 4th.
16x to the fourth times 1.
We would just ignore the 1 because the 1's just going to put it to 16.
Yep.
It's not gonna do
Okay.
anything.
How about 2x cubed?
That would be 4 times 8.
4 times, what is this going to be? Yep, 8x cubed. What's 4 times 8x cubed?
It's going to be 32x cubed
cubed.
y.
Yep, and then we got, don't forget about the y. All right. What's 2x squared?
That would work out to 24xy squared.
So 4x squared times 6. 4 times 6 is 24. X squared, y squared. Michael, what about 2x times 4?
8x and then cubed.
8x,
Oh, never mind. Something.
Y.
y cubed. And then my last term,
This last term.
just y to the 4th. Yep. Okay, so that one involved a little bit more because you had to actually do those product to powers out. Okay, any questions on that? All right, once you get used to the pattern, for low numbers, like maybe up to 5 or 6, this goes pretty quick. It should go pretty quick. All right, let's try 3x minus 2y. This time it's only to the third power. Okay, what's my first coefficient? 1. And what's going to go in parentheses next to it? 3x to the third power. We don't see the second term yet. Plus my next coefficient, 3. In parentheses,
3x to the second.
second,
Negative 2 to the
and negative 2y. Okay, next term, coefficient,
3.
3. Okay, in parentheses,
Just 3x.
just 3x, and in parentheses here,
Negative 2y to the second.
2y to the second. And last term, what's my coefficient? Just 1,
Negative 2y to the third.
and negative 2y to the third. All right, so now let's simplify that. What's 3x cubed? 27. X cubed times 1. Just 27x cubed. Okay, so I gotta do this in a couple steps now. What's 3x squared? That's 9x squared. So now let's multiply all the numbers together. We have a 3 times a 9x squared times a negative 2y. What's 3 times 9? 27 times negative 2. We We have a negative 54, and now we just need our variable. What's going to be my variables on the end? X squared. And what else? Y. Yep. Okay, let's do the next one. What's negative 2y to the second power?
4y squared.
That's a 4y squared. So we have a 3 times a 3 times a 4. What's 3 times 3 times 4? So 36. And what are going to be my letters?
xy squared.
X, y squared. Yeah, that looks good. And my last one, what's negative 2y to the third power?
Negative 8y cubed.
Negative 8y cubed times 1. There we go. Okay, so you can have kind of like the basic ones that we did earlier, just a single factor plus a single factor raised to a power, or you can have ones where you have to do it out in that last step. Okay, any question on that one? All right, let's try one more of those. Still to the third power again. So not as high as the first ones I did, because there's more stuff going on. Okay. What's my first coefficient?
1.
1. And what goes in parentheses?
2x to the third.
2x to the third, that's it. Okay. What's my next coefficient?
3.
3. Okay. What goes in parentheses?
2x to the second.
2x to the second. And what about here?
Would be the bottom. Fifth.
Well, what's the exponent going to be on this?
3. 1.
That's a 1.
Oh.
So that's a 1. And then what goes in the parentheses?
Y squared.
Y squared. Okay. Plus, what's my next coefficient?
3.
3. What goes in parentheses here?
2x to the first.
2x to the first. And what goes in parentheses here?
Y squared to the second.
Y squared to the second. Last coefficient? 1. The 2x is gone. What goes in the parentheses?
Y squared.
Y squared to the
Third.
third. Okay. What's 2x cubed times 1? 8x cubed. All right. Let's do this separate. What's 2x squared? 4x squared. What's 3 times 4? So 12. X squared. Y squared. Okay. Let's do this one. What's y squared squared? That's going to be y to the 4th. What's 3 times 2? So 6. And what's my next letter? X to the first. Y to the 4th. And the last term, y squared cubed. That's going to be 1 y to the 6th times 1.
Yeah, 12xy, can't you technically make it, like, do you have to put the squares on both variables?
The only other way to write something like that would be like that.
Yeah.
That would also be correct. I usually do it out like that. Yeah. 12x squared y squared. All right. So that's how you can expand something with the binomial theorem. So the only limit to this is how high of a row do you need in the triangle. All right? Assuming you can generate the row that you need, the pattern is always going to be the same. The exponent on the first term is going to go down, 3, 2, 1, and then it's 3, 2, 1, and then it's gone. The exponent on the second one First, it's not there, and then it's to the first, to the second, and then to the third. So one goes down, one goes up. It's just getting those numbers that are in front. So we're going to need a better way to calculate coefficients. And most likely I wouldn't ask you to do something like this, even once I show you a better way to do it. Okay? What I would ask you for there is if we were to expand that out, how many terms would be in the total expansion? Yeah?
44.
It would be 44. So what I might do is say, if you were to expand this out, tell me the 17th term. Just tell me one term. You don't have to do the other 43. I just want to know one of them. So as long as you have a better way to calculate the coefficients, we can find the 17th term very quickly. But we need a better way. That's what I got to show you. So to do that, we're going to talk about factorials. Does anyone remember factorials? There we go. Okay, so factorials basically use this symbol, exclamation point. The exclamation point represents a factorial. Factorials are only defined for positive integers. Like you can do that. You can do that. You can do 2 factorial. We're not going to talk about like what happens if you tried to do 3.5 factorial. That's a little different. All right, so this is pronounced n factorial, or the real way you pronounce it is n. That's how you got to say it, because it's got the exclamation point. Okay, so if you want to figure out what n is, okay, n is the product of every number from 1 up to n. So like 5 factorial is 5 times 4 times 3 times 2 times 1. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. So it's the product of every number from 1 up to your number. So factorials get very big very quick. Right? If you even just type in like 10 factorial on your calculator, the product of every number from 10 down to 1, that's pretty big. Okay? And it's under math. I think it's probability, and it's the 4th option down. So you can see 10 factorial is already in the millions. So by the time you get to like 20 factorial, it's already going to be in scientific notation. Okay, that's 2.4, and then there's 18, 20, like 2, and then 18 digits after it. So that's a pretty big number. So what can happen is if you try to type in a factorial that's too big, it's going to just say overflow. And I didn't even type in that big of a number. I just typed in 75. So forget about trying to do like 2,000 factorial or something. It's way too big. All right, so the calculator can't even handle 75 factorial. So that's one thing that we can run into. We can run into a problem trying to type these in. So a lot of times we have to do a little simplifying before we can even put it in, because the calculator can't handle the size of numbers we would try to put into it. Right. So there's some tricks we can do. So it's the product of every number from 1 up to your number. Now, it's a little weird for some of the lower numbers, because how do you multiply every number from 1 up to 0? How do you 1 up to 0? So the definition doesn't quite work for 0 factorial. But what we do is we just define 0 factorial to be the number 1. So 0 factorial is 1. Even the next one, 1 factorial, the product of every number from 1 up to 1, well, it's really just the number 1. But then after this, the definition makes sense. What's the product of every number from 1 to 2? 2. How about every number from 1 to 3? 6. Every number from 1 to 4?
24.
It's 24. And how about the product of every number from 1 to 5? 120. Yep. So any question on the idea of how to calculate a factorial? Remember, the whole point here is we're trying to figure out how can we get the numbers in Pascal's triangle in a more efficient way. Okay, that's what we're getting at. So we're going to use this concept to figure out the numbers in Pascal's triangle. And the numbers in Pascal's triangle are the coefficients we need when we expand something that's a binomial. So suppose that we want to find something in row n, column r. What number did I say we always start with when we're talking about rows and columns in the triangle?
0.
We start with 0. So the notation for finding something in row n, column r, is this. It's these parentheses, and then you're going to see a number on the top and a number on the bottom. The top number is the row. The bottom number is the column. So if I wrote something like this, that means I want to know what number is in row 5, column 2, starting at row 0 and column 0. And the pronunciation of this, we don't usually say, like, what number is in row 5, column 2. The way you can pronounce this is 5 choose 2. And the reason you can say it that way is because this concept also ties in with probability. If you had 5 objects, and I said to you, how many ways can you choose 2 of them as a group? The order you choose them doesn't matter. Like having the red and the black one is the same as having the black and the red one. That's the same thing. So assuming I had all different colors, how many ways can you choose 2 objects as a group out of a total of 5 objects? That's exactly what the number in row 5, column 2 in Pascal's triangle would tell you. How many ways can you choose 2 things from a group of 5? Where the order you choose, that doesn't matter. So we're not going to get into probability, but if we did, we'd be coming back to Pascal's triangle again. Remember, you're always starting with row 0, column 0. So we're not going to go through the whole proof of this, but that is the formula for calculating any number in Pascal's triangle. It's n factorial over n minus r factorial times r factorial. So now if I said to you, what number is in row 50, column 7, that's not hard to find out. You don't have to list out all 49 rows just to get to the 50th. You just have to plug in 50 for n and whatever I said for the row, I don't remember. Okay? You just have to fill this in. Now, because these numbers can get really big, we can't always use a calculator to do it. We've got to simplify a little bit ourselves first. All right, so now I want you to think of Pascal's triangle. Okay, I'm not going to fill in anything that's like values. Think of that. What would this spot be called in terms of what row and what column is it in?
0, 0, 0, 0.
Row 0, column 0. That is the notation for the top spot in Pascal's triangle. And you could calculate what number should be there, if you didn't know, by filling in zeros in that formula. And it would work. What is that position right there?
Row 1, column 0.
So that's row 1, column 0, and this one is row 1, column 1. So what I want you to do now is start thinking of Pascal's triangle in terms of row and column position, not in terms of what number needs to be in those spots, because we can figure out the number if we need to. There's Pascal's triangle with our new notation. Row 2, column 0, column 1, column 2. Row 3, column 0, column 1, column 2, column 3. All right, so how could we expand a plus b to the n now using this idea? If we don't know the row that we need in the triangle, maybe it's too high. Okay, we don't have it written down. All right, when you write your coefficients, what column do you always start in? Column 0. And this tells you what row to start. What here tells you the row you should be looking at? N. Yeah. So this particular one would start in row N. I don't. Lily, did you sign out?
Yeah, I just didn't sign back in.
Oh, okay. Yeah. So row N, column 0. That would be the very first spot you should be looking for your first number. And then, what would be in parentheses next to it right after that? What to what power? Yeah?
The A to N power.
A to whatever the n is. We don't know what it is, but it would be a to the n. And would I see a b term yet? No, it wouldn't be there yet. So we just have a plus sign. Okay. What would be the next coefficient? I'm not looking for a number, I'm looking for a notation. Row n, column 1.
N choose 1.
N choose 1. So the n choose 1. And then what would happen to the exponent on the a? It was a to the n. Now it would be what? It would be a to the n minus 1. It would be dropping down 1. And what would be the exponent on the b? Well, we already have the coefficient. That's n choose 1. But what's the exponent on the b?
Is it not going to have an exponent?
Well, it already didn't have an exponent, so now it has to start having them. What's the first one that this term always gets?
Would it just be first?
Just b to the first. Yep. Okay, let's do the next term. What would the coefficient be? Yeah?
N choose 2.
And choose 2. What would be the exponent on your a now?
N minus 2.
And minus 2. It's going to drop down another one. And what would be the exponent on your b? B to the second. Yep. And you're going to keep going. Like the next one would be n choose 3, a to the n minus 3, b cubed. N choose 4, a to the n minus 4, b to the 4th. You're going to keep going until you get to, this would be your second to last term. Your very last term is when you're in the same row and column. Row 3, column 3, you're at the end. Your second to last one, your column would be 1 before you're at the end. So you'd be at like row 3, column 2. Your exponent on A would be down to a 1. Okay? The A is about to drop off in the next term. The exponent on the B would be 1 below the highest it's ever going to be. Then when you get to the last term, the exponent on the B is now the highest, and the A is gone. And your coefficient is the last row and last column that you're looking at. All right, so that's basically what we've been doing all along. It's just that's a very generic way to write the binomial theorem. Again, this is really the focus of what we want to look at. How do we get those numbers? These are easy. We just follow the pattern. A's go down, B's go up. All right, so let's try to evaluate 6 choose 4 and 9 choose 5. So remember your formula. Okay, what's n in the top one? N is 6, and what's r? 4. So let's convert that into a binomial coefficient. That's what we're finding. We're finding a binomial coefficient. Row 6, column 4. Let's just take a quick look. Row 6, column 4. 0, 1, 2, 3. That's what we should get. Okay. So this is an easy one we could get without doing what we're about to do. But we can verify we're right. Okay, so what would go in the top of my fraction?
6 factorial.
6 factorial over what would go in the parentheses?
6 minus 4.
6 minus 4, which is 2. And then what would go next to it? 4 factorial. Now, watch what happens. We'll remember that one, 9 choose 5. Okay, watch what happens if you expand this out. You end up with 6, 5, 4, 3, 2. You end up with 2 factorial is just 2, times 4, times 3, times 2. Does anybody see like a chunk in the bottom and in the top that cancels out completely?
You can cancel out the 4, 3, and 2.
Right. Whatever factorial is bigger in the bottom, that will completely cancel with what's in the top. 4, 3, 2, 4, 3, 2. If you don't do that, you're going to end up with numbers that are too big to do on the calculator. Okay. Now, all we're left with is 30 divided by 2, which is how much? 15. And that's exactly the number that was supposed to be in row 6, column 4. All right. So let's try one that's a little bigger. We don't have row 9 of Pascal's triangle done out, but we don't need it. Okay. What would go in the top if we were going to do this out? Yeah, 9 factorial. And what would go in the bottom?
4 factorial.
4 factorial.
And then 5 factorial.
And 5 factorial. What's the bigger factorial in the bottom? The 5. So that's going to completely cancel with the top. What would be left in the top if you canceled the 5 factorial from the 9 factorial? Like as a product, what would you be left with? 9 times 8 times 7 times 6 times 5, 4, 3, 2 is going to cancel with that 5, 4, 3, 2.
You might be left with 4, 3, 2 at the bottom.
4, 3, 2. Now, because we're talking about binomial coefficients, you can't get decimals. Everything in the bottom has to cancel with everything in the top when you're done. So what could I cancel the 4 into?
If
8, how many times? Twice.
And we can
What
cancel the 3 into the 6.
Well, we could just, what's 3 times 2?
6.
6. 6. Gone. So everything has to cancel. What's, let's do 9 times 7.
That'd be 63.
63 times
We'd
2.
have 126.
Yep. So if you had 9 objects in front of you and you wanted to know how many ways can you pick 5 of them as a group, there are 126 ways to choose 5 objects out of 9. Where the order you choose the objects doesn't matter. Okay. Any question on that?
Wait, so what does the 126 represent?
It's how many, well, it's the binomial coefficient in row 9, column 5.
Oh, okay.
But in terms of probability, it's the number of ways you can pick 5 objects out of a group of 9 objects. All right, let's try this last one. So I want you to take 2x plus 3y to the 15th. I don't want you to expand the whole thing. All I want to do is find the 12th term if you were to expand that out. If we were to expand this, how many terms would there be altogether? How many? 16. Right? It'd be 16 terms. So there'd be 16 different terms. And I'm asking you for the 12th one.
Oh, it's because you're asking small.
Now, in terms of keeping the numbers straight in your head, it helps to number these like this. This is the 0th term, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. That's the term that I want to know.
15 over 12, 15th row, 12th column.
So yeah, first thing we need is the n choose r. Okay, what row are we working in? Yes, we're working in the 15th row. And what column are we working in?
12.
12. That's why if you didn't start with 0 when you were numbering these, you would have a problem. You would be one off. If you started with 1, then this would have been the 13th, 14th, 15th, 16th. There is no 16th column in the 15th row. You've gone beyond the end of the triangle. So that's why you have to start with 0 to keep it make sense. Okay, so there's your binomial coefficient. What would go in parentheses next to it?
A, B, 215.
So we need an algebraic expression inside those parentheses. Anyone have a thought what goes inside?
2x.
2x. Now we just have to figure out the exponent. What would be the exponent on the 2x here?
15.
15 here?
14.
14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3. So it's 2x to the third.
And then we have 3y to the 12.
3y, and we know the exponents have to add up to 15, so that has to be a 12. All right. Now it's just a matter of figuring out what that is. It's gonna be a big number. So this is 15 factorial over, what's 15 minus 12 factorial? 3 factorial, and what goes next to it? 12 factorial. Which factorial is going to completely cancel with what's in the top? Yeah, if you cancel the 12 factorial, what's left in the top? 15, 14, 13. And in the bottom, you're left with 3 times 2.
It's going to be 455.
And 3 goes into 15 5 times. And 2 goes into 14 7 times. And you said 35 times 13 is how much?
It's 455.
455, okay. So 455. What's 2x cubed? That one we can do pretty quick. 8x cubed. Okay, so we got that one. So I need to multiply that after. And then 3y to the 12th. Well, I don't know what 3 to the 12th is. 531,441. And what's the exponent on the y there?
12.
12?
So we're going to have, since it's asking for just the term, would we include the
So you
x
need
and y?
So we need the 455 times 8 times 531, 441.
It would be.
That should be your coefficient. Not even gonna write that. So there's my coefficient.
It would be 1,934,445,240.
Yep. X cubed y to the
12.
12th. There you go.
Could you scroll up a little bit?
So that's what I'd be looking for. That's the 12th, I think I said 12th term, if you were to do that expansion out. Yep, 12th term.
Truthfully, if you think about it, because we know that we're going with x to the 15th on the right side, if you know what term you're trying to find,
Yeah, there's different ways to keep track of what you're trying to find. You could have started here and said, well, this is 15, 14, 13, so this is y to the 12th. So you can start from either end to figure out the term. Yep. The 3? Because that we had counted, and that would be the exponent when you get down to 12. It would have started at 15, and it would have dropped to 3 by then. And then it would be 2, 1, and then go.
So you didn't do it.
So that's the homework for tonight. Okay, while you guys are at lunch, I'll put a list of topics that will be on the test. Okay, so I'm just gonna pause it, and I'll do that at lunch.
What even is that? Like,
Are you recording live?
Trust